Prof. Ray Durrheim from Wits University.
Right, well, good afternoon all, and thanks to Saga for also inviting me. And here I will talk about some work that I guess I've done and been involved in one way or another over the last about 15 years, and I think it brings together geotech and geophysics very nicely. So this is about geophysics and nuclear power. So just a few facts about nuclear in South Africa. The Safari 1 reactor at Pelindaba research reactor was commissioned in 1965. It's about 60 years old. There are thoughts of replacing it, but it also does commercial work, produces isotopes for medical use. Koeberg Nuclear Power Station, quite an important part to our grid near Cape Town. It was commissioned in 84, and so last year its operating license ended, and so it had to be, application was made to extend it, and that involved quite a lot of geotechnical and geophysical work. Also, we've got uranium resources in South Africa, and we've been a producer of uranium. NEXA, the Nuclear Energy Corporation of South Africa, produced even nuclear fuel at Pelindaba. This facility is now mothballed, but I've heard that there are plans to fire it up again. Hopefully not to weapons grade, but just to turn it out a decent powering our power stations. The pebble bed modular reactor, you probably remember this. Huge sums of money was spent on this about 20 years ago. That's also been mothballed. Rumors are, they tell me that there are plans now to put modular reactors, not necessarily this one, but at some of our coal-fired power stations. So this could be coming on stream in the next few years. We also have what you do with your radioactive waste. Well, our low and intermediate level waste gets put out at Fall Pits in the Northern Cape. Our high-level waste produced there at Koeberg sits in the swimming pool. Okay, so that's a problem. It's been accumulating for 40 years. And also nuclear energy is an important part of our integrated resource plan, which hasn't yet been passed by cabinet, so it's still been tossed back and forth. When you work in this space, here are some people you need to know. Eskom, of course, is the client when it comes to running things like the power stations. The Nuclear Radioactive Waste Disposal Institute they have to look after places like Fall Pits and also apply their minds to what to do with this high-level waste. The Nuclear Energy Corporation, they're in fact one of the few state-owned enterprises that actually makes a profit, and they do it particularly through their medical diagnostics and therapy. But I believe because they run quite a tight operation, that they've been asked to look at, let's say, getting the nuclear fuel production going and also these modular reactors. And then the National Nuclear Regulator is the policeman who makes sure we do this all right. There's the integrated resource plan, and the interesting thing is, as it stands here is that, and of course this is still contested, but that nuclear could be an important part of our electricity future, our energy future. Right, so let's just make a comment about Koeberg. As I said, it was licensed in 1984 to run for 40 years. The license was running out, so either we had to switch it off, which would mean we'd go immediately to, 2 levels of load shedding would be implemented, or else we would hope that we could, in fact, continue to operate it. And a whole series of studies were done, and I and several other people in the room, like Tife, were involved in this, to look at firstly the seismic, the geotechnical aspects. Is it still safe in terms of the kind of seismic activity we would get? Prior to its construction, studies like this were done, but of course in the last 40, 50 years, methods have changed, new data has come in, and so it had to be judged against modern standards. Also, the nuclear engineers looked at the things like the containment vessels, the corrosion, the pipes, and all those things. And there was also a separate study looked at the risk of a tsunami striking Cape Town. After the Fukushima disaster, of course, this was a concern here. Just something to give you an idea of how much power this puts out. When it's running at full speed, it's like 8 Airbuses taking off, at full throttle, and that's running 24 hours around the clock. So there's, in fact, a lot of, it generates a lot of energy, in fact. Right, so how did we go about the geotechnical site assessment for Koeberg? Well, I can't tell you that because it's not yet in the public domain. Hopefully it will be in the next little while. But what we did at Tastepint was very similar, and Bruce spoke about that, and I will just now focus on the Tastepint study a little bit more from the geophysical side. But here you can read, this is the public information document that was published in 2019, 100-page document, and this, of course, just summarized the main findings of the report. And in that 100-page report, there were about 5 or 6 pages that summarized the geophysical investigations. If you had to look at all the technical reports behind this, on which this is a summary, it would be well over 1,000 pages of technical documents, reports, and data. But so you've got a section there looking at the geological hazards, the kind of things that Bruce spoke about, and I will just talk a little bit about the seismic hazard and surface faulting, what the role that people with more geophysical hat would hold. If you want to read about this in more detail, there has been a paper published. You can find it on the internet, and describing the main steps in this process. So where is Coburg? Where's Taceport? It's near Port Elizabeth, just other side is Jeffreys Bay, surface paradise, and also shown on that map around Cape Town is Coburg. You can see there's a whole international team of people who are the team leaders, but on a project like this, there were well over 50 people involved. When you'd have a meeting of the whole team, it would be a bit like we've got right now, that number of scientists and engineers in the room reporting on all their different activities. So these were some of the team leaders. Right. How do we go about this? What standards are there? Of course, in South Africa, our national nuclear regulator doesn't have their own standards because this is an unusual thing. So just like with, I suppose, blast monitoring, they use standards that have been produced elsewhere. And there's the one that is favored and that was chosen to use was those standards published by the United States Nuclear Regulatory Commission. So, and these are called SHAC, Senior Seismic Hazard Assessment Committee guidelines, and this is what was followed. You've got this big team, people playing all sorts of roles. The sponsor, the client, was Eskom. You've got a project management team, and the Council of the Geoscience were the project managers. And then we've got teams that were mixed between South Africans and international specialists who were the seismic source characterization, technical integration team, and the ground motion technical integration team, and giving input to this were a whole lot of specialty contractors, they call it, like SRK would have been in there, resource experts, proponent experts, and I was part of those. And a very interesting thing about this is as part of the SHAC process, you have to have a training in cognitive bias, because we all tend to go through our favorite theory and disregard other things. And so part of it, we have to really investigate the whole center body range of possible technically defensible solutions. And so part of our role there is to be calling each other out and saying, have you considered, or could you think of that, or could there be an alternative interpretation? And that is something I think we could perhaps do more often in our community to alert, so we just don't, and we have things called proponent experts, and those are people that play a different role, and they must become like advocates in the court and defend the theory to the hilt, not be reasonable, but try to really push other people and play that role. So at different times you put on different caps. Sometimes you might be a proponent and you say, no, I'm taking, and so that's not necessarily what I believe, but I'll argue it. Another time you'll put on your resource expert cap. Another time you'll be a member of the PPRP, I suppose that's the Review Quality Control Panel. So it's a very interesting process, time-consuming and expensive, as you talked about. I'm sure a lot of money is spent here, but hey, the consequences are severe and the costs are high. So what you do as geoscientists, of course, you have to look at the geology, and from the seismic point of view, you need to understand where are your faults and which ones of them could possibly be active. So, even when you're looking at a plate tectonic model, you have to decide, is there thin-skin tectonics, thick-skin tectonics? Where do the dislocations run? And so you look at the past, and all that is known about the history. And again, you'll get different people advocating different models to come up with the best range of possible solutions. So you don't just stick for one, you have to consider the whole range of possible solutions. You zoom in closer, the offshore faults, of course, came from the petroleum data that has been acquired offshore, and a lot of faulting has been, of the faults on land, of course, have been mapped by structural geologists in the Cape Fold Belt. And then, of course, sites are studied in a great deal of detail around Cape St. Francis. You find around Taceport, studies were done, and along the fault itself, you're looking for every fault that's exposed. Can you get any indication of when it slipped, how much it slipped, is it active now or not? And even here, a trench was dug in a strategic location across the fault, and some very detailed work was done. And so we just zooming in even more closely. You can see geochronology work being done, the rocks being dated to try to again get the idea of when there might have been slip on that fault and when those sediments would have been deposited to get your best possible model. And just as an aside here, in the trench, they decided that probably here about 10 to 12,000 years ago, there was a magnitude 7.2 earthquake somewhere along this Congo fault. And of course, it happened then. These recurrence periods are large, but it could happen again today. You know, so it could happen. We just do not know. And that's what we try to determine as well as we can. Geotechnical work, of course, the top 30 meters of the near surface is critical when you're trying to look at the response of the site to ground vibrations. And so boreholes are drilled, geology is mapped, and of course, from a geophysical point of view, in this case, the shear velocity is mapped, because that is what controls the intensity of shaking, so shear velocity mapping. And of course, we've spoken about it before. You just have some boreholes, so to interpolate in between, we will use things like MASW to fill in those gaps. Right, and then the other side is you want to look at what is your record of seismic activity. And this is the catalogue, and this work was done by the Council of Geoscience. They run the South African National Seismological Network, but it was only became operational in any decent scale in 1971. So you've got maybe 50 years of data, and you're trying to understand what happened in the last 5,000 or even 50,000 years. So again, you're dealing with a very incomplete data set, and you're trying to hope you base it on that the number of small events will give you some indication of how often the larger events will happen. And so what needs to do in all these aspects, you need to get all the data sorted out, get it to the highest quality, try to decide how you're going to do your source zonation, areas where you've got similar seismic character, both for what we call area sources and fault sources, characterize them as well as you can in terms of a recurrence model. And then at the same time, when you get to your site effect, you have to look at not only the propagation of your seismic energy through the crust over distances of tens to hundreds of kilometers, but also any amplification effects you could get in the near surface, and put that all together and come up with an estimate of hazard. So these are just showing the seismic model that was derived. You can see there are, I think, 5 different area sources like the Central Karoo and the Makwaland. And then there are, I think, 5 fault sources where we had sufficient data on those faults to characterize them in terms of return periods and length of rupture, depth of seismogenic zone. And so those were all subjected to analysis. The data was scrubbed up. And the way you present this is in terms of a logic tree, where you try to, again, consider all the different ranges of these different parameters. So this is the logic tree for the 5 source zones. And you have to decide for each source zone, what is going to be the maximum magnitude that you would expect, what is plausible. What is your recurrence model? I won't go into all these things, but these are the parameters you put in that are going to give you your best possible guess of your recurrence period. How often will any event, any sized event, but particularly a potentially damaging event that could cause damage at your target site, could that happen? Right, and these are summarized. Here you can see our 5 areas. Here are all the different parameters that had to be derived. And you can see these are the curves that we came out on this one axis. We've got magnitude of the earthquake, and that's our recurrence period. And what to me is quite interesting, of course, the green dots are we've actually got data. That's what's happened in the last 50 to 100 years. Of course, you can extend it back a little bit by looking at the news reports and newspaper reports since recorded history, and back a little bit further by looking at paleoseismology. But you can see quite a lot of what we are wanting to do to get our big events is to look at expanding them, where we're getting to get our potentially damaging events, our 6s and 7s. And you can see this is, we practice in quite serious extrapolation, but what else can you do? You can wait another 5,000 years, or you can do the best with what you've got now and take the uncertainties into account. So that's some of our modeling. Exactly the same process was done for each of the fault sources, like the Worcester fault, the Congo fault, and so on, and went through the same exercise of trying as best we could to come up with our parameters, our recurrence rates, and estimate the uncertainties that we have. And again, you can see for each of the faults, the 5 faults, our frequency magnitude distributions. And you can see here they're truncated, and looking at your length of the fault, you estimate what is your maximum rupture length here that you can expect to get. Is it 50 kilometers, 500 kilometers? Because that will give you an upper end to the maximum earthquake size that it can host. So it's really a case of doing the best with the data you've got and coming up with, and here we get into then where we're coming up with so-called mean hazard curves. So in the end, and of course we're considering one site, we're considering Tasman. So we're not making a whole map, we're considering one site, and we're seeing, and also what you do, of course, we do this expecting the ground motion you'll get at different frequencies, because different size structures, depending on their footprint, on their height, respond differently to different periods of vibration. So this can be done across the whole spectrum, but just here to keep it brief, we're looking at a 10-second period and a 2-second period. And we can see the contribution to the hazard made by our 5 aerial zones, our 5 source zones. Of course, those that are close and highly active with big events will make a big contribution. Those that are distant or have small maximum size or infrequent seismicity will make a lower contribution, and we sum it all together to come up with our mean hazard curve. So we're looking at the kind of spectral acceleration that will be exceeded annually, and this is used to assess, what is the level of vibration that would be expected, and then that's given over to, of course, the structural engineers to decide, well, how are they going to build a nuclear plant that can withstand that level of shaking. Right, and this is again summarized, that just useful engineers like to use this. Again, you've got period along the one axis, and on the other axis is our spectral acceleration, in terms of the acceleration due to gravity, say 10 meters per second squared. Right, so that was, but just to summarize the findings, this SHAC level 3 probability seismic hazard assessment was done at Tasman. Tied together with a whole lot of geological investigations, looking at, for example, mapping the marine terraces and seeing if there's any evidence for offsets of the same terrace that could have been related to historic faulting. Extensive geological mapping, but generally it was found that most of the faults, they are non-seismogenic under the current tectonic regime. Of course, in the past they were active. Maybe if the tectonic regime had to change, and that could become active again, while others generally had a low probability of hosting a major earthquake. Also, the seismic record, the seismic catalog was quite sparse and had gaps in it. But looking back to over a few centuries, there's and seeing the records and reports of seismicity and earthquakes in that area, of course there was some. This is some interesting stuff to do, but it was sort of confirmed that this is generally an area of low seismic activity. And then importantly, a whole lot of VS measurements were done in order to really help characterize the amplification, if any, that you will get on the site. Right, then just a few comments on the end. Radioactive waste, what do we do about that? And as I said before, there is a site that is in fault pits, some 100 kilometers away from Springbok, out there in the flactes of Bushman land. And several of us put together work that has been done over the last 30 or 40 years, and this was published in 2023, the December issue of the Journal of South African Geology. So geologists, geomorphologists, seismologists, and Mary Evans, who's our optically stimulated luminescence lab manager, so looking at some of the dating of these things. That's the site, the area, a bit of geology on the left. So it's mostly, you see the granite gneiss bedrock of Namakwaland and covered by some very youngish sediments. On the right is an aerial picture showing it's a far bigger area than this. It's mostly a nature reserve, but areas now where trenches are being dug, because over here, the low and intermediate level waste, and this is stuff with half-lives of a few hundred years or so not very hot, put in steel drums and buried in clay layers is the situation that we have here. And picture on the left, just the general geology, the granitic bedrock underneath, and on top we have these clayish layers, lenses of sandstone and silt in between. And then, of course, these trenches, when they're dug down to depths of about 5 meters. They give you a very nice opportunity to map that. And then Marco Andrioli spent a lot of time in the hot Bushmanland sun mapping those edges of those trenches to see whatever structures he could come up with. If there's any evidence, for example, of there having been an active fault in that region. And Studying the whole geomorphology in the region, there is evidence, we believe, for there having been seismic activity, slip along faults. And on the right hand, you see 3 sections. But the important thing to see those sections, there's huge vertical exaggeration. The horizontal axis is about 10 or 11 kilometers, and the vertical axis is maybe 20 meters. So, I mean, when you're out there, it just looks like flat as a pancake. But when you look at digital models, there is evidence that there, of a fault scarp that extends for perhaps 20 to 25 kilometers, and over a little bit of a zone. And that's just because of the name of the area. We have named it it's named as the Symp fault zone. Strike length, just a bit more than 20 kilometers, throw of perhaps up to 5 meters. At its closest point, 8 kilometers to the fault pit site. Okay, so the question is, if an earthquake had to happen 8 kilometers from the fault pit site, and we put high-level waste there, what level of shaking would you have? Is there a chance that it caused the release of radiation into the atmosphere? So that's the question that was being asked. And so we looked at, and this is more the seismological side, we gathered whatever seismic data we had. We put in and ran several additional seismic stations in that area. And in all, we had for over a 20-year period, 89 to 2009, we had 457 events within 100 kilometers of fault pits, and we were able to do our normal standard seismic analysis, came out with the idea that our source of our seismicity is in the upper crust, depths of perhaps 4 to 10 kilometers. Our B value, that's really the ratio between your bigger and smaller events, very much used in your recurrence calculations, of about 0.8. And the maximum magnitude that we would predict in that period was around a magnitude 6. And these actions, when you look at it on a more regional scale, you can see there's a broad zone of highish seismicity for Southern Africa anyway, which is shown on the Council for Geoscience seismic hazard map, running about 900 kilometers northeast to southeast and 200 kilometers broad, which has got from time to time swarms of activity happen. And just last Christmas, just before Christmas, there was a magnitude about 5.5 earthquake which happened near Brandvlei. Brandvlei is the nearest place with a dot on the map. And you can even see some videos that were in some of the farms had of chickens flapping at the night as they got startled by the ground shaking. But anyway, so there is seismicity that happens. There are clusters in this whole Namaqualand regions, like at Grabis and Leeugamka, and this is the type of seismicity we get there. But to put it all together, looking at empirical earthquake parameter relationships, a 22 kilometer long rupture, okay, is consistent with an earthquake of about a magnitude 6.3. In some ways, you can take the 1969 series Tulbach earthquake as an analog. It was of that sort of magnitude and that kind of rupture length. But the average slip, and this would be for a normal fault that you get for a 6.3 earthquake, is only about a quarter of a meter, 20, 30 centimeters. And so in order to get a cumulative, a slip of maybe 3 or 4 or 5 meters, the implication would have been that it would have been repeated earthquakes over quite a long period of time. And we're looking back maybe 60 or 70,000 years ago. So these are questions. It raises some questions. If this is going to be a high-level nuclear waste site, well, we'd certainly need to do a bit more work to characterize it, to make sure how safe or unsafe it is. And what we would need to do that is really to resolve some of these issues, perhaps do more closer, more detailed, sensitive seismic monitoring, but also clearly to dig some trenches along these postulated fractures along the Symp fault zone. So really that gets me to the end of it. So I say, look, there seems a good chance that there might be a development of nuclear power here in South Africa over the next decade or two. Who knows really what will happen? But if that does happen, we'll certainly need input from skilled engineering geologists and geophysicists, both to select the sites for these power stations and also to dispose of whatever radioactive waste they may produce. Thank you.
Thanks, Ray. Any questions? Oh, lots of questions.
Thanks, Ray. I have 2 questions. One was a project that I was also involved in. Why are we writing off a piece of land instead of using old underground deep infrastructure as nuclear waste? Because, this is going to be a written off piece of land for thousands or tens of thousands of years to come. Secondly, I have seen the names that are listed there, and most of those people are quite senior. It's in the sense of what sort of training and what sort of route do people have to follow for them to become part of that panel members?
Yeah. Well, first on the, let me answer the second question first on this Coburg nuclear investigation. It was seen as an opportunity to train young staff members. So people like Tife were on the technical teams and other people of the similar generation. So there was a very deliberate effort to involve younger geoscientists, seismologists, and geotechs in this project. So it was also seen as a training opportunity. And I guess I think that's great. In terms of where to dispose, well, I mean, here in Bushmanland, while it might be a large 10 by 10 kilometers area, it's an area with not much economic activity going on. While in deep mines, of course, you might interact with the water table. They might be closer to areas of human habitation. But one of the big issues is you can't just look at the site itself, the disposal site. It's how do you get your waste from where it's been produced to where it's stored and things like that. So you have to look at the whole route. And so in that sense, and I mean, this is a big problem in Europe, when you're transporting waste from where it's been produced to the disposal sites, say in Germany, where they put it in salt mines and things like that, and goes through villages and towns and across level crossings, railway level crossings. And so the tendency in countries like Sweden and Finland is you have your disposal on the same site as your nuclear power station. You build your nuclear power station on granite with few fractures. The community there is used to, most of them are nuclear workers. That's how they make their living. They're comfortable with it, and you don't even take it off site, or at worst, you take it by ship along the edge of the Baltic Sea, so it doesn't interact much with the general public. So there are many considerations as to what we do to dispose of this. But internationally, you either put it in clay, you put it in salt, or you put it in hard rock. Okay, we don't have salt layers really in South Africa, so it would probably be one of the other two. But then big things are, where do you have your site, your new power stations? You want them near to where your consumption is, or else where you have transmission lines. So some of these modular reactors may go into the power stations where the coal is mined out, and you already have your cables, your wires running out of there, while others will be near maybe Gqeberha or Durban or Cape Town, which are big sources of consumption. But then you've got the issue of where to put the hot stuff. Yeah.
Thank you for the nice presentation. I want to ask your opinion on the Vaalplaats radioactive waste site. So since December, I would say from December until May, there's been consistent swans that are occurring in that area. Do you think that can be a result? Is there something happening below the surface in where the radioactive site is situated? Another question I have for you is, you talked about trenching that you did. On the trenching that you did, I'm interested to know, did you see was there any displacement exposed? Did you see any offsets? And
yeah, there are two things. The firstly,
another one.
Yeah.
The last question I have for you, you also mentioned about you foresee trenching into the fracture zones. What would you be, I'm interested to know, because I have I would say I have a knowledge in knowing that when you trench in normal fault or strike slip faults, at the shallow, you'll be able to see offsets. But now you've mentioned something different to me now. Fracture zones, what can be exposed when you trench into fracture zones?
Okay, firstly, in terms of, is there any connection between the current disposal of nuclear waste at Vaalplaats and the recent swarm of seismic activity? No, it's just coincidence. But I mean, the recent swarm is typical of what we get in the whole Namakwa-Natal belt. And that's why we, in fact, have got data from the Council for Geoscience. One of our honors students here is looking at the whole, the modified Amori law, looking to characterize it and see what it can tell us about seismicity in that region. And it's not only of interest for us in terms of the disposal site, it's also of interest, should any fracking take place in Karoo sediments above these kind of rocks, could it trigger a dangerous earthquake? So we're very interested in seismicity in our basement in that area. Then you asked me about, now you'd have to give me a key word.
And then I asked you about trenching.
Trenching.
Yeah.
Yeah. Now,
And the depth and the exposure.
Yeah. So Marco did, those trenches are maybe 5 meters deep. He looked at it in a great deal of detail and he saw evidence of thrusting and things like that in those trenches. But now, again, you get all sort of soil pedagogy. What's the wrong word? The soil phenomena happening in soils, as soil swells and shrinks and collapses. And it's quite difficult to decide, whether these thrust-like features were actually caused by tectonic scale faults or just more local soil mechanic issues. That's, I think, it's a little bit of an open question. And if you read the paper, we discuss it, or the people who know about it, the geomorphologists and the geologists discuss it at depth. But also when you're talking about if you had to trench across where we think the fracture zone is just a generic term we use in that paper for a fault zone. And you'd expect as you go down, you might see the fault strands. You might be able to see evidence of when there was slip. You find a marker horizon. Then you look for, you sample that, try to see when that was last exposed to the sunlight, and that will give you an idea of the age of when that slipped. So yes, you'll dig a trench. It would be maybe 10 meters wide. It might be 5 meters deep. It might be 200 meters long, and in you go, the geologists, and they map and see what they can find.
Cool. Thank you, Ray. Thanks very much. One last round of applause.